We have analyzed the gain of the common source amplifier using drain feedback biasing and found the constraints for the gate bias resistor RG. Now we will do the same thing for the capacitors, coupling capacitors C1 and C2. Okay. Now this on the left side is the complete circuit with drain feedback bias and also the input source connected through C1, the load coupled through C2, and the small signal equivalent is shown on the right side. All I have done is to open circuit I0, short circuit VDD, and replace the transistor with its small signal equivalent. Okay, and this is what we have. So let's see what the capacitor values must be so that they do behave like short circuits. This is the circuit we have, and first let's focus on C1. Okay, and the input source of course is deactivated. The principle we use is as usual to find the resistance that appears across the capacitor and make sure that the capacitive reactance is much smaller than that resistance. And in this process the independent sources in the circuit are shorted. So the input source Vs is shorted to ground, and also we have two capacitors, and we don't want to get into the complication of calculating with both capacitors in place. So we will make a reasonable assumption that while calculating the value of capacitor C1, the other one is chosen correctly such that it does behave like a short circuit. Okay. So we will replace C2 also with a short circuit while carrying out calculations for C1. Okay. So now this is the circuit we have, and here are the two terminals of the capacitor, and just for completeness I will connect it up like that. Okay. So what is the resistance that appears across C1? Let me draw a box around the rest of the circuit. This is ground, by the way, this point is grounded. So if you see, the C1 is connected between this terminal A and terminal B. Okay, and between B and ground there is the circuit enclosed within the box. Okay, in other words, I have C1 over here, RS, and this is connected to something that's actually the circuit, and there will be some looking in resistance. Okay, you know that if you have a linear circuit, then the equivalent between any two terminals will be a resistance. Okay, so there will be some resistance inside. Okay, and this resistance is nothing but the input resistance of this circuit. What do I mean by that? When you have a circuit, a two port, okay, some two port 1, 2 and 3, which is common ground, let's say, we have Vs and Rs and RL on the other side. Okay, in such a situation, the resistance that you see into the input port, that is between this terminal and this terminal, this is known as Rn, and between this terminal and this terminal, this is Rout. Okay, that's the output resistance. And the output resistance is computed with Vs being set to 0. Okay, so this is the definition. If you have something that you can identify as the input port, then the resistance looking into that is the input resistance, and something that's identified as the output port, resistance looking into that is the output resistance. It's important to remember that while calculating the input resistance, the load must be in place. Okay, because this can affect the input resistance. After all, it is to the right side of this circuit. Similarly, while calculating the output resistance, the source resistance here must be in place. The source itself would be set to 0, but the source resistance would be in place. Okay. So between these two terminals, between this point and that, it's nothing but the input resistance of the circuit. So this also kind of gives us an experience of calculating input and output resistances of amplifiers. Okay. And across C1 you clearly see that we have Rs plus Rn. RS we already know, Rn is what we have to calculate. Okay. So let me put down that part of the circuit again. This is the gate, drain and source, which is grounded, and across this we have RL. This is GM VGS, where this voltage is VGS. Okay, and we have to calculate the resistance looking into these two terminals. And you know from basic electrical circuits that the way to do it is by either connecting a voltage source and measuring the current that is flowing through it, taking the ratio, or applying a current source, finding the voltage that develops and taking the ratio. And in this particular case, I will connect a voltage source V test and find the current I test. Okay. So all we have to do in that is to write the Kirchhoff's current law here. In fact, I would encourage you to stop the lecture right here and find this I test and the ratio V test by I test, which will be the input resistance. Okay, so please do this by yourself. I will show you the answer, but of course it will be a better learning experience if you do it by yourself. Okay. So if I write Kirchhoff's current law equation here, let me call this VO. Okay. The voltage here is V test. I have V test minus VO by RG. That's the current being pumped into the output node through RG. And that current will be equal to the current that is flowing out of here, which is GM VGS. And you see that VGS is exactly the same as V test in this case. So it's GM times V test plus VO by RL. And you also see that this current I test here is nothing but the current flowing through RG. So I test equals V test minus VO divided by RG. And you can eliminate the variable V0 from these equations and find V test by I test. And hopefully you have tried this by yourself and you got it correctly. And the correct answer is RG plus RL divided by GMRL plus 1. Okay. So that's it. You would have chosen some value of RG, and based on that you can find this Rn. Okay. And as far as our capacitor C1 is concerned, C1 should be much greater than 1 by omega naught times Rs plus Rn. Okay. If I write it in terms of reactances, the reactance of the capacitor 1 over omega naught C1 must be much less than Rs plus Rn, and in terms of C1 it's like this. Okay. So C1 has to be much more than 1 by omega naught Rs plus this whole quantity Rn, Rg plus RL divided by GMRL plus 1. Okay. And you can see that although this Rg will be very large, this GMRL is also a large number because it's the gain. So the input resistance will be substantially smaller than Rg in this case. Okay. So from this you can calculate the constraint on C1 and set C1 to be, let's say, 10 times or even more compared to the constraint. Okay.